Probably get a message. All right. Welcome back, everyone. I hope you had a great summer so far. And this is the first long-range colloquium LRC after a little break we had over the summer. So let me very quickly remind you of the context of this series before I introduce our speaker. So the LRC is a colloquium series that is being run by the Virtual Science Forum, whose aim it is to facilitate online meetings like workshops, talks, the seminar series. You should check out our website. If you Google Virtual Science Forum, you'll find us. And we do everything online, and incidentally, that started before the pandemic. So this is not an initiative that started because of it. We were way ahead. It's completely volunteer run, the VSF, the Virtual Science Forum. So everything we do also is open source and it's publicly available. If you want to know how those emails that we send get automatically created and sent, you are welcome to find our GitHub page and join our effort. Any ideas or volunteers, more than welcome. And all of that is in very large part due to support from the Kavli Institute of Nanoscience in the TU Delft in the Netherlands. So to kick off this first after break LRC, we have today with us Richard Kueng from Kueng, I should say, who's an assistant professor at JKU, the Johannes Kepler University in Linz in Austria. And Richard has traveled the world. He studied at ETH and obtained his PhD in Germany. And then after some postdocs in Germany, he did a postdoc at Caltech. That's where I had the pleasure of meeting him. Richard studies a very interesting intersection between three large fields, namely that of computer science, physics, and applied math. I think, in my opinion, today's colloquium is going to be an awesome example of that intersection. So I look forward very much to hearing more about provably efficient machine learning for quantum many-body problems. And if you have any questions, please use the raise your hand feature or type in the chat, and then I can interrupt Richard and ask your question. So with that, Richard, the screen is yours.
Hi, thank you very much for introducing me and also for actually organizing this open source seminar. I think it's a really, really good idea, and I'm really, really honored to be allowed to speak to you today. And I'm going to talk, as Ebert already pointed out, to some rather new results, where we try in a nutshell to do something interesting with near-term quantum devices and machine learning, but with the twist that we have the ambition of actually proving something about that. So like kind of proving that this idea is fruitful and can actually work. And this is the result of a long and very fun and intense collaboration. And I feel very privileged to have worked with such amazing co-authors and collaborators. So I want to briefly mention all of them. There's Giacomo Torlai, who is now at Amazon Web Services. There's Victor Albert, who is now at the University of Maryland. And I think he's actually attending the talk right now. And Victor, maybe later in the talk, when there's going to be some physics questions, I might have to relay them to you because they fall more into your area of expertise. I hope this is okay. And then there's John Preskill from Caltech, whom most of you, I guess, undoubtedly know. But really, the main contributor is Robert. He's in Huang from Caltech. This is really kind of, he's the mastermind behind these ideas today. And I think like most of the credit should go to him, credit where credit is due. And yeah, I already hinted at that, like kind of as Ebert pointed out, I actually work at the intersection of math, computer science, and physics. And so I'm kind of like familiar with statistical learning theory, and this will be important throughout the talk. But towards the end, when we talk about quantum phases of matter, it is entirely possible that many of you actually understand more about this material than myself. So be warned. And here's like kind of the teaser of my talk. Again, we want to combine machine learning and quantum computing. And there's many possible ways of combining them, but we take, I would say, a rather conservative approach where we try to combine the main strengths of both fields. So in particular, we will use quantum computers to simulate interesting physics that we will then use as data in order to train classical machine learning procedures on conventional supercomputers. So the quantum computers are responsible for simulating interesting physics, and the classical computers are responsible for actually carrying out all these amazing machine learning techniques that have really changed a lot of our lives in the last couple of years. And so here's kind of an outline of my talk. I first actually want to spend quite some time on illustrating the general idea and putting the pieces together in order to get at a question, at a meaningful and hopefully interesting question that involves machine learning, training data from quantum experiments, and a learning procedure that is well posed in the sense that we can actually hope to prove that a thing like this should work under reasonable assumptions. And then I will segue into like what I would call the main application, which is our first main result, which is about predicting ground state properties, where I think we've managed to arrange all the pieces in a way that actually allowed us to do just that. And I will also go through the main theorem and kind of tell you what kind of assumptions we need and what kind of results we get. And then I will also want to talk about a second application where we take inspiration from image classification or supervised learning, which is very powerful, but we try to apply it to learn something interesting about quantum physics, and more precisely want to distinguish a trivial phase of matter from a quantum phase of matter. And again, if you arrange things correctly, then it can actually prove that this works under reasonable circumstances. Okay, so here's the general idea. Like broadly speaking, we want to use machine learning to learn something interesting about quantum many-body physics. And the twist will be that we will empower this package by data that can be taken from a quantum experiment. And so kind of here is the stereotypic problem that I want to use to illustrate our approach, but also which will include the first main result. And it's the many-body ground state problem. I think it's the canonical problem of quantum many-body physics, where you start with a macroscopic description of a Hamiltonian. So here you can, for example, see a hexagonal lattice. And then if we assume nearest neighbor interactions and maybe a Heisenberg Hamiltonian to be concrete, then kind of there's like coupling strengths between nearest neighbors. And the strength of them kind of like, and there's additional real numbers that tell us how strong these individual interactions are. Like how strong is the XX coupling, how strong is the YY coupling, and how strong is the ZZ coupling. But importantly, if we have n qubits or n spins here, n spin 1/2 particles, and let's say nearest neighbor interactions, then there's only polynomially many interactions. So for n qubits, there's polynomially many couplings, and each of them is specified by a real number that tells us how strong it is. So the input is a string of polynomially many, let's say, real numbers. And that's important because it's something that we can keep track of efficiently. And then the question is, view this as a quantum many-body Hamiltonian and somehow compute a classical representation, or at least properties of the associated quantum mechanical ground state. And this is suddenly not such an easy problem anymore, because if we were to directly compute it naively, then we would have the problem of the curse of dimensionality, right? If we have n spins here and it's a quantum system, then there's at least 2 to the n degrees of freedom. And the Hamiltonian is a 2 to the n by 2 to the n matrix. And if you wanted to find the ground state, the lowest eigenvector, we would somehow have to diagonalize an exponentially large matrix. And that is expensive. But if you come more from a computer science angle, there's actually also deeper reasons. There's complexity theoretic obstructions. If you could solve this type of problem for, let's say, a bit contrived input Hamiltonians, then you could encode very, very stereotypical computer science problems like the satisfiability problems into a special case of such a problem. And it is widely believed that these problems are hard to solve in the worst case. So kind of if we want to directly go from a macroscopic classical description of the Hamiltonian to the ground state, then this is a difficult problem. There's many good ideas on how to solve it for instances, but in general, it's difficult. And kind of the twist that we want to look at, and of course, this is also well known, is what happens if we don't do just a direct computation, a direct algorithm, but if we do something that allows us to maybe learn from previous models in a type of a learning setting. So now kind of the problem is still the same. we are given a Hamiltonian, a description of a many-body system, and we want to bring ground states or properties thereof at least. But now we have some additional information, some additional advice, and the advice we envision is kind of ground state properties or ground states, classical descriptions of ground states that belong to Hamiltonians that are somehow similar. So think of a random Heisenberg Hamiltonian on this lattice, for instance, and suppose that we already kind of have computed, or at least, or maybe even simulated certain types of this Hamiltonian and know what the associated ground state is. And we did that like many times already. Then this is additional advice. And maybe it's entirely plausible that a new instance, even if it's different in the fine structure of the couplings, maybe overall it will behave kind of similarly, at least if you're in the same quantum phase of matter. And this is the promise that machine learning has. It kind of allows you to be empowered or like to benefit from already solved problem instances that look similar. And kind of in order to get a bit of quantum computing into that, you can also go a bit further and actually maybe envision that the quantum data or like the type of training data, the type of ground states, it doesn't have to be constructed by solving an algorithm like that, because this can run into exponential bottlenecks. You could also envision a near-term quantum computer that kind of takes the Hamiltonian as an input and then cools down the system and produces the actual associated ground state as an actual quantum state. And then the question is kind of, can we still use that and kind of extract classical information, strings of bits that we can then use to train a machine learning procedure like a neural network or a support vector machine to kind of learn a function that can take a new Hamiltonian as an input and produce a classical representation of the ground state, or at least interesting properties there. So that's the high level picture. But of course, there are challenges and questions associated with that. The first question is this actually paying off? Does it make sense to do such a generalization? Can classical ML that benefits from training data actually solve problems that just a simple direct computation could not? And the short answer is yes. There's actually also computer scientific reasons for that, but also the sheer success of artificial intelligence in the last decade should tell you that like really there's really power in data. And these types of algorithms can be very powerful. And then two more questions, like one of them is actually, I just want to emphasize that shortly, we have to be careful about the type of output we actually want to have. We have to like maybe think a bit about what the result of our computation should be. Because if we naively insisted on getting an exact representation of the ground state, then this would be a bad algorithm design, right? Because it is an exponentially large matrix. And in the worst case, it might just take exponentially long to write it down. And then we can't hope to do it efficiently. So it's important to have something on the output side that is actually efficiently computable in order to ensure that the entire thing can in principle be efficient. And the other thing, which is also interesting, is if you take this perspective of imagining that the data you actually use to train your machine learning model has been generated by quantum experiments or quantum computers, then you actually need a way to convert this quantum information into classical strings of bits, right? Like kind of your experimental friends, they will not hand you an exact classical representation of the ground state. They will give you a spin system and say, this is the ground state. And so the question is, how can we efficiently convert these physical ground states into strings of bits that carry enough information, enough meaningful information in order to empower a machine learning procedure? Okay. And in a nutshell, the project we did, our paper and the talk today is about answers to these questions. And here I kind of already gave one, at least on a high level. Yes, if you have additional information in form of training data, then your algorithms can become strictly more powerful than if you did a direct computation. And on the output way, we also, I think, found a way of how to classically represent ground states in a way that you can write them down efficiently and store them efficiently, but they still tell you something interesting, but they will tell you something interesting about local features in this example. And the last, and maybe the most important link actually, is how do we read in training data? How do we convert the physical ground states in the laboratory to strings of bits that a machine learning procedure can actually use. And the method we use there is called classical shadows. And the underlying idea is that randomized measurements, randomized quantum measurements, can actually provide you with a very efficient quantum to classical converter. And the idea is if you have an actual physical quantum system, then you perform some sort of simple random evolution on it, single qubit on each spin, a very simple evolution, and then you perform a single shot measurement. And in our case, the simple evolutions will be simply, I either measure in the x basis, in the y basis, or in the c basis, and each with equal probability. And kind of what this does to the individual spins that I've tried to visualize with this Bloch sphere here is that the original, kind of like an original Bloch sphere vector, is going to get forced to align with one of 6 directions on the Bloch sphere. One for x, one for y, and one for c. And this happens for each of the qubits. And so by collapse of the wave function, if you perform such a measurement, you collapse the quantum system to a classical string of outcomes, namely one of 6 symbols, which of the 6 is aligned with, and there's one for each qubit or for each spin. And this collapse of the wave function ensures that after we did the experiment, the quantum system is kind of destroyed, but we got one string of outcomes that we can store efficiently. Because again, it's a string of n symbols. And then what is important to realize, and that's just the postulates of quantum mechanics, is regardless what the original quantum many-body state was, for instance, a ground state of a certain Hamiltonian, the information, all information about that quantum many-body state is actually encoded in the distribution behind those outcome strings. Like each of these, there's 6 to the n possible outcome strings, and each of them comes with a certain probability. And this probability depends on the underlying quantum system. And it's actually kind of enough to fully characterize it. That's Born's rule. But this actually segues, gives you the, yes, Anton?
Yeah, sorry, it's a very basic question, but I think it will slightly help me understand. So the basis that you list here is not orthogonal. Yes. The 6 states. Do you mean, do you have something like a POVM measurement or?
Yeah, exactly. It's like the way I presented it, it's a POVM measurement, but like operationally what you would do is you would first toss a classical dice.
Yeah, okay.
If the outcome is 1 or 2, you measure in the Z basis. If the outcome is
all right,
3 or 4, Y basis, 5 or 6, C basis, and then you get exactly such a thing.
Thanks.
Okay, but the kind of the information, interesting information is encoded in the distribution of the symbols. And now what is important to memorize is that we actually, by performing such randomized measurements, we can sample from that distribution. We can create these bit strings. And this paves the way for efficient Monte Carlo approximation, right? In Monte Carlo approximation, we have distributions, and we want to approximate the mean or something generic behind these distributions, or the distributions themselves. And in order to do that, we sample from them, and we do that several times. And then we average in order to approximate the true expectation value, the true mean behavior. And in Monte Carlo sampling, if it gets intricate, then maybe the sampling process is expensive. But in this case, the quantum computer can do it for you. And so kind of you ask your experimental friend to cool down your system to prepare the state. And then you do one of these randomized measurements, and you will get a bit string. And then you repeat that a fixed number of times. And this will give you a Monte Carlo approximation of the underlying quantum state, regardless of what the quantum state is. And now maybe the interesting thing is that this Monte Carlo approximation converges much, much quicker than you might think. And this is prior work by Robert Huang, John Preskill, and myself that was published last year. This is where we coined this term classical shadows. But suppose that you're not interested in reconstructing the full quantum many-body system, because remember, that's exponentially expensive. You might not be able to afford even reading out the solution. Let's say you look for something more simpler. Let's say you're happy with accurately approximating the quantum system on local smaller subsystems. So in this example, we have a square lattice, like a rectangular lattice of 36 qubits or spins. Let's say we are only interested at accurately approximating the reduced density matrix, the subsystem operators, for kind of regions of size 4, but all of them. And then you can actually prove that in order to get an accurate description for all of these subsystems simultaneously, the number of Monte Carlo samples you need scales exponentially, but it scales exponentially in the subsystem size. And it only scales logarithmically in the total number of qubits. And that's going to be important because that's kind of what our efficient quantum to classical conversion actually is. We construct these efficiently storable Monte Carlo approximations in order to approximate the subsystem in order to approximate subsystems and not the entire system. And this will ensure that we don't run into a coercive dimensionality and kind of the total system size only enters logarithmically. Okay, is there maybe a question at this point, or is everything clear? In case you want to know more, John Preskill gave an excellent talk about these kinds of ideas at the Simons Institute, and the talk is also available on YouTube. But I'm happy to take questions now also. Yes, Anton?
So in this setting, you consider, you disregard the complexity of preparing the ground state, yes, because for a general bad Hamiltonian, yes, that is also computationally hard.
Yes, that's a very, very good point. And thanks for keeping me honest, because part of the reason why machine learning is powerful for difficult problems is that you can outsource the difficulty of computing to the difficulty of generating training data, right? So that's in a way that's not surprising because the Hamiltonians you envision, they should be difficult. But I still would say that there is a potential window of opportunity where we have cooldown processes that maybe a near-term quantum computer could do, but which might still be hard for our classical devices. And that's kind of the window of opportunity where I want to get. Does this make sense and answer your question, Anton?
Yeah, absolutely. Thanks.
And I think there was another raised hand.
There's two more. I think Raimel Medina was first. Please go ahead.
Hello, do you hear me well?
We hear you very faintly, I think. I do hear something. Try again.
Now, better now?
Not much better.
Much better? Okay.
No, not much better. How about you can try to figure that out or maybe type your question, and then in the meantime, we can perhaps ask Joseph Tyndall to ask his question first.
Thanks for sure. Sorry.
Just a quick question. This the time it takes to sort of sample, recreate the size R subsystem, is that contingent on the subsystem being purely local, or
no,
can that be?
Excellent question.
It's
just easier to draw, but it works for any type of subsystem, even if it's like one particle here and two there and one there again.
Okay. Wow. Okay. Yeah, that's really interesting. Thank you.
And you really do get all of them together.
Okay. Yeah. Nice.
That's kind of where the power of this type of Monte Carlo sampling comes from.
Yeah. Okay. Brilliant. Thank you.
Raimel,
okay.
Do you want to have one more slide? Otherwise, type the question, and then I can ask it for you. Assume you're typing. Go ahead, Richard.
Okay, but kind of this is like the essential link, I would say, that allows us to wire a hypothetical quantum computer that does the cooldown procedure to generate data to a machine learning setup. And so the idea is, again, we want to have like kind of a machine learning algorithm, not a direct computation, that can be empowered by data, and the data can undoubtedly be generated by computing exact diagonalizations or doing DMRG or whatever you know. The important thing is that the actual training data, the representation of the ground state, is such a classical shadow, such a Monte Carlo approximation, because it is efficiently storable. It is kind of presented in the way a classical computer likes it. And as I showed you before, kind of like very, very rather short Monte Carlo approximations already kind of locally represent the entire quantum system. And the hope is that this is enough to actually empower the machine learning procedure to learn an efficient functional relation between a new input Hamiltonian in our example that we haven't seen yet, and it will empower it to actually present us with an efficient classical description of the new associated ground state. And tacitly, we will also assume that this new classical representation of a ground state will be presented as a classical shadow. So again, it will be kind of a Monte Carlo approximation that features these strings. Okay, and here's the spoiler. If you impose reasonable assumptions, at least I would argue that they are reasonable, about the types of Hamiltonians, then you can actually prove that this works. And before telling you about the theorem and the assumptions, let me try to demonstrate that this can actually work by means of a simple yet illustrative example. And the example we considered is a random Heisenberg model in 2D with an antiferromagnetic signature. And we did it on a square lattice with 25 spins, as you can see here. Yes, Ebert?
Before you dive into this, the question from before is now in chat. So Raymond wanted to ask how random your unitaries have to be.
Very good question.
Classical shadow. Yeah.
In our case, they have to be a single qubit basis rotations that are independent. So I have to tell qubit 1, I have to be able to rotate qubit 1 to measure it in the x basis, for instance, while at the same time telling qubit 2 to be measured in the y basis. So I need single qubit control, but not more. And I really only need Hadamard's or like the other basis transformation that gets you into the y basis. So I would say it's rather limited when it comes to classical randomness and the difficulty of actually implementing it, but it's still not trivial. Okay, and now back to our first application, the two-dimensional Heisenberg model with 25 spins. And here, again, our vision is that we generate training data by kind of sampling Hamiltonians from a certain family, in this case, a random family, and we just achieve that by taking each of the nearest neighbor couplings and sampling it uniformly from the interval between 0 and 2. So kind of in the end, there will be a coupling for each of the nearest neighbor connections in our Hamiltonian, and it will be a random number. And this will give me a Heisenberg model, and then I can kind of do direct exact diagonalization or DMRG. In our case, this is a numerical study to compute the associated ground state classically and exactly. And then if we can do that, we can also simulate this Monte Carlo sampling, this quantum measurement. And this is precisely what we did here. Kind of we did, in order to generate training data, we sampled 90 of these random Heisenberg Hamiltonians at random, computed the associated ground state, simulated a randomized measurement in order to get a Monte Carlo approximation, but a very crude Monte Carlo approximation where we only used a single string, like the sample size 1. It's kind of interesting. It's enough for these purposes. And we did that 90 times. And then we fed it into a very, very simple machine learning model, an extrapolation model. I'm going to tell you later what it was. And this gave us a new formula that where the input is couplings from a new Hamiltonian, and the output is an actually more accurate Monte Carlo approximation of the associated ground state. And here's kind of, you can see the empirical performance for a new Hamiltonian that is actually visualized here. Kind of the thickness here is the actual coupling strength for the test Hamiltonian, the new Hamiltonian we sampled. Here is a similarity matrix that tabulates the two-body correlation between any pair of different spins. So a 25 by 25 matrix where kind of color, where the intensity and strength is color-coded. So that's the exact value from doing exact DMRG computation. And on the right-hand side, you see what our machine learning model actually predicted. And it is a bit different, but if you look at it, it looks really similar. And this on the right-hand side was really an efficient computation. It was a simple to evaluate function that takes the new Hamiltonian as an input and outputted all these correlators, all these two-body correlators. And in order to do that, we needed a training data size of 90. Okay, so empirically, I hope I could convince you that this type of setup actually works. And now let's switch gears a bit and enter into math territory, because our first main result is actually that we prove that such a type of learning procedure has to work. And with most mathematical theorems, you need some assumptions in order to ensure that it works. And so let me sketch the assumptions first. And just to get the language right, lowercase n is the number of qubits or spins. In this case, it was 25. And the other important part is the parameter vector x that tells us, that characterizes the Hamiltonian. So in our case, x, in this case, x is, let's say, the string that incorporates all nearest neighbor couplings. And this would be, I think, a vector, an m-dimensional vector. Here I wrote -1, 1, but here it would be between 0 and 2, each of the values. And there's 1 for each nearest neighbor. So I think the total number is maybe linear or quadratic in the number of spins. So it's kind of m is polynomial in the number of spins. And then we also need to specify the target. Remember, because I once said that we have to be careful not to ask for too much, because if we ask for an exact representation of the full ground state, that's an exponentially difficult problem. And so we do something simpler. We ask to actually accurately represent a simple linear function in the actual ground state. So x is the parameters, are the parameters that specify my Hamiltonian. Rho x is the associated hypothetical ground state. And let's say that O is a linear observable that only depends on size R subsystems. So kind of, we look at local properties and we have an additional parameter R that tells us how large these local properties are. Think entanglement entropies as an example, or like kind of, no, not because they're not linear, but think of two-body correlations as we pointed them out here. That's a concrete example. And then the one really important mathematical assumption that we need is that the function that actually takes the Hamiltonian input parameters, in our example, all the different coupling strengths that we have newly sampled, and maps it on the expectation value of this local and linear observable, has to be sufficiently smooth. In the sense that kind of if you differentiate it, it is well behaved. But this is arguably a bit of a mathematical property. And I want to point out that very, very physical many-body physics properties actually imply sufficient smoothness. So one way to ensure that this function is smooth enough for our theorem to work is to assume that our Hamiltonian describes a spin system in finite spatial dimensions that experiences or enjoys a constant spectral gap across the entire parameter regime. So we are kind of well within one phase, for instance. And this is the case here, for example. And this in particular ensures that the function is sufficiently smooth and that the most important mathematical assumption is actually met. And then there's another non-essential assumption that makes the math a bit easier. We also assume that the training parameters are sampled uniformly. Kind of here, this was exactly the case, because for each new training instance, we sample all the couplings uniformly at random. And that means that each new training data point, each new Hamiltonian is kind of sampled from the same distribution. And the last thing is that in a quantum to classical conversion, in the representation of the training data ground states, we assume that the ground state that belong to the training parameters are converted into classical shadows into Monte Carlo approximation that only contain one sample. So it's really just one single string of outcomes that represents our training data. And under these assumptions, we could prove that the number of training data, like the number of examples you need in order to learn a function that generalizes nicely to new examples, is quasi-polynomial in the number of degrees of freedom, in the number of parameters, which is in our example, the number of nearest neighbor interactions. And if the training data size is as such, so it scales quasi-linearly in the number of parameters, then we can write down a very, very simple extrapolation procedure that actually takes all the Monte Carlo approximations we've seen already. These are kind of the classical shadows of the training data, and it convolves them, it combines them in an actual linear fashion in order to produce a new Monte Carlo approximation of the new ground state. X is now kind of a new parameter range, and it enters in this type of simple kernel function. So for a new type of parameter, this is a simple linear formula that combines all the classical shadows, all the we have already seen, in order to give you a new kind of Monte Carlo approximation of the new ground state. And this is efficiently storable, and then you can use this row hat in order to compute the new function. And the actual guarantee we provide is that on average, over all possible parameters, of all possible new parameters you want to know about, new materials, the approximation error of our linear observable is smaller or equal than epsilon. And it is also important that kind of everything is efficient in a computational sense. And this is also true. Kind of the cost here of actually training this model, it's just a linear extrapolation model. This is efficient. And the cost of evaluating it for a new one is also efficient. So the total cost of actually running this procedure is linear in the number of spins, and again, quasi-polynomial or quasi-linear in the number of parameters. And in a way, this mathematical theorem just confirms what we've seen before, namely that this kind of approach actually works. Are there questions at this point? Yes, Anton?
So I would like to understand better the how practical is the smoothness assumption. Let's say one is dealing with an unknown Hamiltonian, which is hard to predict. So is it possible to how under which circumstances would it be possible to guarantee the smoothness, or at least estimate whether it is satisfied on a given family?
That's a very good question. And I think it would depend. I think the best way to do that is to look at it on a case-by-case basis. Because like with Hamiltonians that you actually care about, there's a lot of additional structure that we didn't assume in this theorem. For instance, we didn't even assume here that the Hamiltonians is a sum of local terms. We looked at very general families. And then we observed that a constant spectral gap is enough. But you're rightfully pointing out that this is maybe limiting the range of the applicability of the theorem. But there I would actually say that take your experience and have a look at the smoothness condition and just try to like find your own way of figuring it out. Okay. Just on this level, and just very quickly, something about the proof idea behind this argument. The way we formulated the actual prediction procedure, it's not really a machine learning procedure, it's a linear extrapolation model. And it actually looks a lot like a Fourier transform once you think about it, because this kernel function looks really like a Fourier transform. And this is not arbitrary, because in a nutshell, what we do in order to prove that is we really capitalize on the assumption that the function is sufficiently smooth. This is the most important one, because in a mathematical sense, this tells you if you have a smooth function, you can do its Fourier transform. And if you have a smooth function and the Fourier transform of it is effectively band limited. So kind of like you can do a cutoff, and you make a very small mistake. You make a very small error if you do a cutoff, and you can choose the cutoff not too large if you're sufficiently smooth. And that's kind of the underlying idea. If we are sufficiently smooth, we can do a Fourier transform, we can do a cutoff, the error is not that large. And then subsequently, how do you approximate a band limited function? Well, the answer is, of course, Nyquist's theorem, right? You do another Fourier transform and you start sampling. But this is precisely what we do here, because the training data is generated randomly and gives us kind of like samples from the original basis in the original domain that we can then use to glue together the band limited function. And the last ingredient we need is that we never work with the true ground states, because that would be too expensive. But we work with these Monte Carlo approximations with these classical shadows. And they concentrate so nicely that the convergence happens very rapidly. And we only need a single sample for each of the training data points in order to get the convergence to a level where this average approximation error is true. And this is the proof we present in the paper. It's really kind of a harmonic analysis inspired proof. But recently we found out that a more difficult proof strategy also extends to neural network learning techniques, to infinite width neural networks. you can also prove it for them, and the empirical performance is even better. But here for this theorem, it's harmonic analysis. Okay, and you can now start to play around and do a bit more numerics. In this case, we looked at a one-dimensional Rydberg chain. These Rydberg systems are very fashionable these days. It's kind of quantum simulator platforms. We did numerics for a one-dimensional chain with 51 atoms. And I don't want to go into details, but these Rydberg arrays, they're kind of specified by a Hamiltonian that forces kind of like the Rydberg atoms can be in a ground state or in an excited state. And kind of the Hamiltonian is such that you don't want to have two Rydberg systems, two excited states too close to each other. But there's some tuning parameters in this type of Hamiltonian. In particular, there's a detuning, and there is an interaction range between the different Rydberg systems. And so this is a type of Hamiltonian where we have a one-dimensional chain, but there's only two parameters that are relevant. And so we can kind of like the parameter range is a square. And if you actually look at it, the associated ground states of the Hamiltonians belong to three different phases. One of them is a disordered phase, one of them is a C2 ordered phase, and one of them is a C3 ordered phase. So kind of here, we have a simpler system because we only have two parameters, but we have interesting physics happening in there. We have three different phases. And so we just empirically tested how important this sufficient smooth condition actually is. Because if you think about it, the function here can only be sufficiently smooth if we stay well inside one phase and never approach boundaries. But here in this example, we just tried what happens if you do it. And we generated training data points, and you can see them here in the two-dimensional diagram. These gray circles are training data points, and we generated 20 of them. Kind of like this is the systems we simulated, the Rydberg system we simulated. We created Monte Carlo approximations thereof. And then we did this type of approximations. And then we actually saw, and we tested it on three new points, the star, this shape, and the cross, and see how well we approximate the local poly X and poly Z expectation values. And as you can see, it worked out remarkably well. And so this empirically demonstrates that at least for these types of rather simple Rydberg systems, you can actually combine training data from different phases in order to get more accurate prediction about new types of Rydberg systems. Okay, and so numerically, at least, this showcases that maybe the constant spectral gap is not essential to guarantee sufficient smoothness. And Anton, maybe this is interesting for you. I don't know. Maybe it's a bit reassuring. Okay, but with that, I want to switch gears a bit and briefly talk about the second application we consider, and that's a binary classification problem. Like when most of you probably, when you think about machine learning or you hear your colleagues marveling about it, then the stereotypical application is always binary classification. You have cats and dogs, and you feed the machine images of cats and dogs and tell them this is a cat, this is a dog. And then somehow the machine learns to distinguish them. And if you hand them a new picture, then it can often reliably tell you whether this is a dog or a cat. And kind of we want to play the same game, but a bit with a quantum physics spin, and maybe a non-trivial one, where we want to teach a classical machine learning model to distinguish a trivial quantum phase of matter from a topologically ordered quantum phase of matter, for instance. And so the empirical example I want to use to motivate that is how can we distinguish a topological quantum phase of matter from a trivial phase of matter. And what do I mean by this? Like for the trivial phase, we assume that a product state, an n-qubit product state, no correlations, is an exemplar of the trivial phase. It's a trivial state. And then we start populating the trivial phase by applying short depth random circuits to it. So that's a quantum computing inspired way of thinking about phases. But we start with a stereotypical state and then populate the phase by applying short depth random circuits. And our exemplar for a topological phase is Kitaev's story code ground state. And in our case, we look at 200 qubits or examples. And so this is a 10 by 20 lattice. So the exemplar state for the topological phase is Kitaev's story code ground state on a 10 by 20 lattice. And so the code distance is 10. And in order to make this problem more interesting, we start to apply random quantum circuits of increasing depth to them to explore the two different types of phases. And so the machine learning question is binary classification. So kind of we have a classical machine and we feed in examples from either the topological phase generated in such a fashion or the trivial phase generated in such a fashion. And we tell them this one belongs to the topological phase, the other one belongs to the trivial phase. And then the learning model should itself find a strategy of how to classify a new state where we don't provide a label. And again, an important question on how to do that is how should we feed in the training data? And we again assume, because we can't fit in realistically like kind of a topologically entangled state with a full classical description. And so again, we use this classical shadow concept, but this time we need more Monte Carlo samples. We assume that the input is a label that tells us which phase it belongs to and a Monte Carlo approximation with, in this case, 500 different samples. And then we actually come up with a new support vector machine, it's called, kind of like we take these Monte Carlo approximations and map them into a very high dimensional feature space. And we actually handcrafted the feature map to play nicely with these classical shadows. And in this high dimensional feature space, the hope is that the examples from two different phases actually cluster very far away from each other. And the first plot here actually showcases that this is the case. Because here, what we've plotted is kind of on the x-axis, that's the circuit depth we use to populate the phases in our example. So in circuit depth 0, there is no circuit. And it really is either a product state or guitar historical ground state. And so this actually tells you, we map it into the high dimensional feature space, and then we do a principal component analysis, a one-dimensional one. That means in this high dimensional feature space, we look for the direction of largest variance, and then just look where the 2 points fall to. And here you can see that all the trivial points cluster here, and all the topological points cluster here. That kind of tells you that the feature map, the mapping in the high dimensional space, does what it should do, at least if there's no quantum circuits. And then things get interesting if you start increasing the circuit depth. So this is circuit depth, number of layers, over the code distance, 10 in this case. So this is kind of a ratio that goes from 0 to 10. Then you start to see that the phases become populated. And the trivial state starts to hide itself behind ever increasing random circuits. But you can still see that this high dimensional feature map embedding does a pretty good job up to like maybe circuit sizes that are roughly half the code distance or the correlation length of the topological phase. And at the very end, where the circuits are as large as the code distance of the torical ground states, you cross the two phases and the two exemplars become indistinguishable. So kind of this showcases that a binary classification scheme can actually work, even in the unsupervised setting. Here we really did the most naive thing you can do with these high dimensional feature spaces. And if you do actually smarter things, like for example, train a convolutional network in this high dimensional feature space, or do some support vector machine, then you can see that the classification accuracy for new examples actually stays very high, even for large circuit depth. And long story short, I just want to convey that we can use a similar philosophy, use classical shadows to represent quantum states, kind of as Monte Carlo approximation, in order to teach a machine learning model to distinguish between toric code ground state type quantum states and product state type quantum states. And our second main result actually tells you that under reasonable assumptions, this works. Yes, Ebert?
Sorry, I just had a very quick question. If you had any insight into why the convolutional network doesn't work, is that here just because of the low amount of...
No, here's the problem. It's actually kind of, it's very devious. Kind of what the CNN, the supervised CNN does, is in this case, you train it on the outcome distribution of a 6 outcome POVM. So kind of what the difference is that in our methods, we use the classical shadows as input to the procedure. Whereas this original work, CNN supervised, they use the outcome distribution. And now, regardless what you do with your learning method, if you start inputting the outcome distribution, then your data is always linear in the underlying quantum system, right? Because the outcome distribution is. And then these short circuits fool it. Because it's impossible to have a linear function that distinguishes a topological phase from a trivial phase. That's what makes them interesting. And this is why the original convolutional neural network is just as good as random guessing.
Perfect, thanks.
Okay, but so like the second main result is a bit similar to the first one. We have some assumptions, and then the theorem actually tells you that what I just told you here has to work. And it has to work so efficiently. And the assumptions here are maybe a bit more contrived, because the first assumption, or like maybe actually not, because the first assumption that we need here is that a phase classification function actually exists. So kind of we assume that there is a certain function in the quantum systems, like a topological entanglement entropy, for instance, that is capable of resolving the binary classification problem. And I think like at least conceptually, this makes sense, right? Because if no such function exists, then maybe we are not really in different phases. And maybe there's not like a clear distinction that a machine learning model can actually learn. So kind of we have to assume that there's a nice phase classification function that again doesn't depend on the entire system, but only on subsystems of certain size. And the example you should think about is topological entanglement entropy, where the subsystem size is a bit larger than the correlation length. Because it's like kind of a sum of logarithms of like systems that only need to be a bit larger than the correlation length, but can in principle be independent of the total number of spins. And then a second assumption we need is that the training data are that we get n exemplars of one phase or the other that are labeled, and they are represented by classical shadows, by Monte Carlo approximations that now have t different samples, not just one, but more. And we also get labels, and we assume that they are correct. And then essentially what our second main result tells you is that if you train a so-called support vector machine, which means you go into this high-dimensional feature space and find a separating hyperplane up there, that's what happens. Then a support vector machine is capable of reliably distinguishing the two different phases for a new Monte Carlo approximation of a quantum state you haven't seen yet, that is promised to belong either to phase 1 or phase 2, provided that the size of the Monte Carlo approximations you process is exponential in the subsystem size you hypothetically would need to resolve the phases. And the training data size scales polynomially in the number of qubits, but it scales kind of like nastily with the subsystem size again. If this is the case and the underlying phase classification function exists, then you can prove that such a binary classification procedure must work. And I think this is still interesting because we never have to assume that we actually know the phase classification function. So in a way, the machine learning procedure actually finds it by itself. So if topological entanglement entropy would work, then this support vector machine would either find it or find a function that is similarly good at distinguishing the phases. Okay. And we did some additional numerics where we looked, for example, at the bond alternating XXC model. And there again, we did, I would say, some fun example computations where we have now, again, kind of like a quantum, this is now a quantum many-body system, and we look at two different parameters that we can tune in this bond alternating XXC model. And depending on how you tune them, there's three different phases. One of them is a topological phase, one of them is a trivial phase, and one of them is a symmetry broken phase. And in order to test how robust our idea and our feature space actually is, we looked at data points that actually traverse a single line. For instance, here we kind of like the training inputs were exemplar states that followed this line. And then we mapped each of them, the classical shadows of each of them, into the high-dimensional feature space and did a PCA again. And as you can see, principal component analysis, that's again unsupervised learning with the largest 2 dimensions only, already clusters the 2 faces. That kind of, here you can see what the topological invariant would tell you along this path. And here you can see the same color-coded points in the cluster relatively nicely across a trivial phase and a topological phase. And when you cross the phase transition, you can see these outliers, but you can actually determine them. And something similar is true if you traverse all 3 phases and you get a picture that looks like this. Again, not even with supervised learning. Just going into this high-dimensional feature space and doing a principal component analysis is enough. And with that, I'm actually at the end of my talk. I want to thank you very much for your attention. And I just quickly want to remind you that I tried to tell you something about the intersection between machine learning and quantum computing or quantum experiments. And I guess we can all agree that there's a lot of potential. There's also a lot of potential combinations of how you could like try to arrange the 2 fields or topics. And we tried to combine them in a relatively conservative way, I would say, where we tried to use the well-known strengths of the 2 approaches. We wanted to use quantum computers or quantum experiments to generate training data in the hope that they can generate training data about interesting physics that we couldn't simply simulate on a classical computer, at least not cheaply. And then we used classical computers and powerful existing learning techniques like neural networks, for instance. We can use them or support vector machines in order to actually learn from these training data points. And this will hopefully allow us to extrapolate and directly compute interesting things about new physical systems that we haven't seen yet. And I think the interesting twist is that we didn't only do numerical studies, but we also came up with provable guarantees that showcase that this type of combination can be fruitful and it can provably work efficiently under reasonable assumptions. And again, I think there's actually a window of opportunity for near-term quantum devices. I think we should use the quantum simulators and the quantum computers we built today to generate interesting training data, and then use classical machine learning models to extrapolate. Thank you.
Thank you very much, Richard, for this wonderful insight. You had a bunch of questions during your talk already, but perhaps there are more. So if you have any questions, now is the time to ask. Or while you're thinking of questions, perhaps I can start with some. Feel free to type questions or raise your hand, by the way. So there are 2 things that I was wondering about, actually. They're not super related, but perhaps most importantly, I wanted to ask if you had considerations or considered non or incorrect labels. And I guess the bounds that you're listing assume that everything is labeled perfectly.
Yes.
Whereas in computer science, I'm sure you're aware of these results also, especially with neural networks.
Yes.
You can actually get away with a whole bunch of random labels
Yes.
in your training set. I assume that would influence the number of samples you need, or perhaps not. I don't know if you've thought of that.
We haven't done the math yet, but I would argue that kind of the math behind that is relatively general and powerful. Kind of like it's one of these general statistical learning theory results that come from powerful mathematical statements. Exactly. That can actually empower arbitrary kernel methods. And I think those have been studied, and you can extend them to correct for, let's say, a certain ratio of wrongfully labeled data points.
Yep.
But we haven't done that yet.
Okay.
And kind of empirically, I think, although we didn't do it here either, we didn't kind of like randomly permute the labels here, but you can actually see that kind of it is a bit stable when you do tricky things.
Yeah.
Like crossing a phase.
Here though, this was with hand-designed feature map.
Exactly. This is, I think, was really, really remarkable. Robert came up with a new type of kernel function that is really based on physical intuition and these Monte Carlo approximations.
Yep.
We call it the shadow kernel. And it's efficient. That's important, right? With kernels, they can be very powerful, but sometimes they're very complicated or expensive to evaluate. But essentially, it's a doubly exponential kernel that compares individual strings of this form. And this is why it's efficient. And kind of the double exponential ensures that you can actually kind of approximate, you linearize all possible polynomial functions, because you can write every polynomial function as a linear function on a tensor product, right? Mm-hmm. And at the same time, if you kind of like cleverly sum over all possible subsystems, you can also kind of like take into account all of them. And Robert realized that if you kind of like cleverly arrange these things, the sum over all kind of polynomial degrees becomes an exponential function. And the sum over all possible subsystems also becomes an exponential function.
Another exponential, yeah. Right.
And I think that was a really cute insight, because you come up with a double exponential that just compares, that just a string element by element comparison between these simple strings.
Yeah.
But there's this underlying intuition that it linearizes all possible polynomials and all possible subsystems. And so topological entanglement entropy, for example, looks like a nice linear function in this space.
Perfect. There are 2 questions in the chat, and I'm wondering perhaps, Charles, if you would not mind unmuting and asking. Otherwise, I can read the question. But...
Sure. Thanks, Richard, for the nice talk. I was just wondering, so on the classical shadow side, in this way of doing random poly measurements, it has this cost of t is scaling exponentially with r. I'm just wondering, so suppose, but that also encodes a lot of information, for example, that I may not care about. So for instance, if I only care about, say, our spatially local subsystems, and I don't want to think about, anything that's like very are local, but not spatially local. Is there a way that I can perform, choose a unitary ensemble or perform measurements such that, the scaling isn't as bad as exponential? Or is there some information theoretic lower bound that you cannot do any better than this?
Well, that's an excellent question, Charles. Let me try to give you 2 answers. Like in the easy case, let's suppose we stick to the single qubit measurements I try to advocate, just because we maybe don't want the quantum hardware to be too expensive. If you do that, you don't save much by restricting yourself to contiguous regions. Kind of like in the end, it's a counting argument. And there's just like the number of total subsystems of size r is not that much larger than the number of contiguous subsystems of size r. If you have an exponential suppression, this is how this argument actually works. But now you're raising an interesting point, because your question, I think, becomes relevant if you start questioning these randomized single qubit measurements, right? I started out with explaining this quantum classical conversion as doing a single qubit rotation on each to effectively measure along 3 possible axes. And this is something you can very much question. And if you're interested in contiguous regions, then you could hypothetically envision different types of random measurements, where you, for example, start scrambling, for example, only these 4 guys and then these 4 guys, and then keep doing that. And that, then it could potentially help. And then maybe for some features or some functions, you might get rid of the exponential there.
Great.
Does that answer your question?
Yep. Yeah. Thanks a lot.
Great. Yanis, from the chat, would you mind asking your question, or would you prefer me to read that?
I can ask.
Go for it.
Yeah. So thank you. Thank you for a great talk, Richard. I wanted to ask, do you encode environmental conditions like temperature, magnetic field, etc.? And then what if they change? Do you need to retrain your system?
Those are excellent questions, Yanis. Like first and boring and honest answer is we didn't take noise corruptions into account yet. Kind of like neither in our theorems nor in our numerical studies. But the things we do, the mathematical proof techniques we use, they are not crazy. They are typically stable with respect to small imperfections. Like small things like measurement noise or kind of like over and under rotations, they shouldn't be a problem. Things get more interesting if you kind of confuse labels here. But I also think that you can argue that this remains stable. The non-zero temperature question is a very important one from a practical perspective. And again, we looked in at least our mathematical descriptions and the numerical experiments, we assumed that we have the exact ground state at 0 temperature. But I think that the method should also be stable for having thermal fluctuations and thermal states that are slightly above 0. But I don't know how far you could go. This is something I haven't looked at it, not at least. I also think that it is possible to actually use a second layer of machine learning procedures to mitigate the noise or counteract it, at least in practice, because that seems to be very successful in near-term devices and the experiments we do today. But in a nutshell, it's an interesting question. And I think that's the most interesting question you raised. And I also don't know the answer yet, but like what happens if you train for a certain temperature and then your sample pops in and it comes from another, right? Because this is a case that we haven't looked at it yet, because like kind of maybe this means that like all your training data is from one side of the parameter space and suddenly you get something that is a bit further away. And that's actually not clear to me. And there like the mathematically rigorous support becomes a bit weaker, because somehow in order to get a rigorous theorem, what you need is that the training data is comparable to the new type of data you actually want to use for predictions. Because otherwise you could start into problems where you train on apples versus oranges and you get Spider-Man. And then like I think mathematical results can't deal with that. But how it works in practice is a different question. And I think it's a very, very interesting one. So Yannis, yeah, you're asking all the right follow-up questions.
Thank you.
All right, there is one more in the chat from Isidora. Do you perhaps want to ask this question yourself too?
Yes, thank you. Thank you very much for the nice talk. I wanted to know whether you can comment on the guarantees needed to classify SPT phases, because I recall that the paper says that your machine learning model may be useful for the classification of these, but what is it that is like missing in this case?
Is Victor still listening? Because I would like to defer that question to him actually. He has a way more qualified answer, I'm sure.
Sorry, can you repeat? I was trying to comment on the previous question.
Yeah. So I think I recall the paper says that your method may be useful to classify SPT phases. But so my question is, what do you need to guarantee in order to be able to classify these?
Well, the existence of a local classifying function is the important part. And the reason we say that there's hope regarding SPT phases is because there's a lot of heuristic knowledge in the literature that such local classifiers exist. So by local, I mean some observable or some more complicated function whose support doesn't blow up in the thermal limit while still being able to resolve different phases. And then why I say heuristic evidence is because a lot of these types of functions do require to have their support blow up to really show rigorously that they work as classifiers. But if you do numerics, those same papers do numerics, and they see that you don't really need some extensive support observable to really get the phases more or less correctly.
Okay, so but as long as this function exists, then you can apply this method.
As long as the function exists, the ML, if it's designed well, should be able to find it or something maybe more fine-grained even. Yeah.
Okay, thank you.
Thank you too, Victor. Good hearing you.
Okay, I see that there's follow-up questions in the chat, and unfortunately, if I stop this meeting, that chat is no longer accessible. How about Yannis and Victor, if you're still interested in that, you continue that discussion via email. And then with that, I think, thank you very much again Richard, for joining us today. And I hope that everyone has a wonderful rest of their morning, day, night, and see you all again for the next LRC.
Thank you. Bye.
Bye.